Hi guys, in GATE lecture series, let us discuss GATE question on direct mapped cache memory. This question taken from GATE CSE 2021 Set 1 question paper. Let us see the question. Consider a computer system with a byte addressable primary memory of size 2 to the power of 32 bytes. Assume the computer system has a direct mapped cache of size 32 kilobytes and each cache block is of size 64 bytes. That means the size of the main memory is 2 to the power of 32 bytes and size of the cache memory is 32 kilobytes and the size of the cache block is 64 bytes. Now we have to find the size of the tag field from the given data. Let us understand the principle of cache memory. Cache memory is a fast, small memory used to store frequently accessed data so that we can reduce the data access time and to increase processing speed. The cache memory is between the main memory and the CPU. So, whenever CPU wants some data, it refers to cache memory first. If the required data is not available in cache memory, then only the CPU will try to access the same data from the main memory. Let us understand the implementation of direct mapped cache memory. For simplicity, I have used a very smaller size for main memory and cache memory. In the main memory, there are 8 blocks and each block contains 4 bytes. That means the size of the main memory is 32 bytes. In cache memory, there are 4 blocks and each block contains 4 bytes. So the size of the cache memory is 16 bytes. Now we will see how mapping is done between main memory and cache memory in direct mapped cache memory concept. That means the address used to access the data in the main memory is the same address is going to be used to access the data in cache memory. So mapping is to be done between the main memory and cache memory using the concept of direct mapped cache memory. Now you listen here. So there are 8 blocks and each block contains 4 bytes. And in cache memory, so it has got 4 blocks and each block contains 4 bytes. So when you want to find the cache block for the particular main memory block, we are using the formula main memory block number mod 4. For example, if we take 7 mod 4, 3. That means this block has to be mapped to the third block in cache memory. So like that you take 4. So 4 mod 4, 0. So this block has to be mapped to the 0th block in cache memory. So that is a concept we are going to use it. But you should remember that we already seen cache memory is a very small memory to store the frequently accessed data. So at any point of time, this cache memory can contain only 16 bytes of data. Okay, so now we'll see how mapping is done here. So main memory size, what we have seen, 8 into 4, 32 bytes. So that means what is the length of the address? 2 to the power of 5 means 5 bits address is required to access this main memory. You may have a doubt in this direct mapped cache memory implementation. For example, we take the scenario, we want to store this block in cache memory. That means 5 mod 4 is equal to 1. So this block will be mapped to the first block in cache memory. After some time, we want to store this block also in cache memory. So what will happen? 1 mod 4 is equal to 1. So this block is also mapped to the same first block in cache memory. So what will happen now? So in this direct mapped cache memory, so what will happen? The content stored in this block is restored to the main block, and the new data will be copied to this first block. So that is what we call it as collision. So when collision occurs, so what will happen? The old content will be restored to the main memory block and the new content will be stored here. Now let us further discuss the mapping process. So we already seen the main memory size is 18 to 4 32 bytes. That means we need 5 bits address. So in this 5 bits address, the last 2 bits will be used as offset. So what is these 2 bits? Actually, what is the size of each block in main memory and cache memory? It is 4 bytes. So to access these 4 bytes, so we need 2 bits. That means, for example, we want to access this particular byte, second or third, like that. So how many bits you need? 2 bits, because the block size is 4 bytes. So to access 4 bytes, we need only 2 bits, because 2 to the power of 2 is equal to 4. And what is this index? This index will specify what is the block number in cache memory. So how many blocks are there in cache memory? 4 blocks. So what is the size of the index? 2 bits, because 2 to the power of 2 is equal to 4. And the remaining one will be used as tag bit. So this tag bit will uniquely identify the particular block. So let us see the example. Let us consider this scenario, that is, this block has to be moved to the cache memory. So how to find the cache memory block number? The formula is main memory block number mod 4. So 4 mod 4 0. So this block has to be moved and stored in this block, that is 0th block of cache memory, because the formula is 4 mod 4 0. Now what about this particular byte? So what is this particular byte? So you just count it. This is 0, 1, 2, 3. Then 4, 5, 6, 7. Like that 8, 9, 10, 11. Then 12, 13, 14, 15. So this is 18 actually. So the address for the main memory is 18. So 18 is converted into binary. So that is 5-bit binary, because the main memory address is 5 bits. So in this binary digits, the last 2 digits represent the offset. So what is this 10? That means 10 is 2 actually. So that is third place, 0th place, first place, second place. So that means third location. And this 00 indicates that index. That means 0th block in cache memory. And the important point is tag field. So what is the purpose of tag field? For example, you assume this block, 0th block. If I consider this block also, again it will refer to the same 0th block. But what is the difference is, the tag field will be 0 for this case, tag field for this case is 1. So the tag field is used to identify the main memory block uniquely. So let us see the tag field. So the tag field 1 specifies this particular main memory block. So this is the way the mapping takes place in direct mapped cache memory. Let us consider another scenario for implementation of mapping in direct mapped cache memory. For example, so this location, actually this block, so this block has to be moved to the cache memory. So as we have applied the formula, here also you apply main memory block number mod 4. So 2 mod 4 2. So that means this block has to be moved to this block here, that is second block in cache memory. Let us talk about this particular byte. So what is this particular byte? That is 0, 1, 2, 3, 4, 5, 6, 7. This is 8, 9. So that is 9 is the address for main memory for this particular byte. So let us consider the 5-bit address for the value 9. So here you see that, so this is the binary value for 9. So here, as we already discussed, the last two digits represents the offset. So offset means 0, 1 means 1 actually. So here we start counting from 0. So 0, 1. So this is the location where the byte will be copied. And what about these 2 bits? That is 1, 0. This 1, 0 means 2. That is, this 2 represents the index of the cache memory block. That means second block in cache memory. And another thing is the tag bit represents 0. That is, the tag bit is 0 for this particular block, which uniquely identifies the main memory block here. To summarize the mapping address calculations in this direct mapped cache memory system, we can find the length of the offset from the number of bytes in each block. Suppose here each block contains 4 bytes. So the offset length is 2 bits because 2 to the power of 2 is equal to 4. Like that, the length of the index can be calculated from the number of blocks in cache memory. So how many blocks are here? 4. So again 2 to the power of 2 is equal to 4. So the length of the index is 2. So how to calculate the length of tag field? So what we can do? We can add the length of the index and length of the offset. That means 2 plus 2, 4. Subtract it from the main memory address length. So here what is the main memory address length? 5 bits. So 5 minus 4, 1. So tag bit length is equal to what we can do? Main memory address length minus what we have to subtract it by the sum of index and offset. So each block of main memory maps to only one cache line. That is, here cache line refers to a block in cache. So if a block is in cache, it must be in one specific place. So what is the advantage? It is very easy to implement. Then what is the drawback? Since more than one memory block is mapped onto a given cache block position, the collision may arise for the particular position even when the cache is not full. How to solve it? We can solve it by allowing the new block to overwrite the currently resident block. Now we understood direct mapped cache memory system. Let us try to solve this problem. The main memory size is 2 to the power of 32 bytes. It is given in the problem itself. And the cache memory size is 32 kilobytes. And each cache block is of 64 bytes. Now we have to find the size of the tag field. So let us find the main memory size, that is 2 to the power of 32 byte. So that means the address length for main memory is 32 bits. Next, the cache memory block size is 64 bytes. That means to access each byte in cache memory block, that is the offset address is 6 bits because 2 to the power of 6 is equal to 64. So the offset address is 6 bits. Now the cache memory blocks, how many blocks are there? The size is 32 kilobytes. 32 kilobytes means 32 into 1024 bytes, which is equal to 32,768. It is already given that each block is of 64 bytes. So the number of blocks will be 32,768 divided by 64, that is 512 blocks. So the address for cache line, that is to access the particular block, that is index length is 9 bits. Why it is 9 bits? Because 2 to the power of 9 is equal to 512. So now we found the offset address length and index address length. So what is the tag field address now? That means the main memory address length 32 minus offset address length is 6 and index address length is 9. So 32 minus 15, 17 bits. So the answer is 17 bits. So offset is equal to 6 bits, index is equal to 9 bits, and tag is equal to 17 bits. That is the final answer. Let us see the next question. For a direct mapped catch, 4 bits are used for the tag field, 12 bits are used for index into a catch block, and size of the catch block is 1 byte. That means each block contains only 1 byte. Assume that there is no other information stored for each catch block. Which one of the following is correct option for the sizes of main memory and the catch memory in this system? So now the address lengths are given and we have to find the size of the main memory and cache memory. So what is the tag field length? It is already given 4 bits. What is the length of the index? It is already given 12 bits. And each cache block contains only 1 byte. That means we don't need any more information to locate the particular byte because each cache block contains only 1 byte only. So the offset length is 0 bits. So from this, what is the total we can calculate? That is 12 plus 4, 16. So 16 bits. So hence main memory size is 2 to the power of 16. That means 65, 536. Okay, that is 65, 536 divided by 1024 because we have to express the answer in terms of kilobytes. So 64 kilobytes is the answer for main memory. What about cache memory? So index is 12 bits and offset is 0 bits. So that means 2 to the power of 12. That is how many blocks are there? 2 to the power of 12 blocks are there. That is 4096. So 4096 divided by 1024 because we have to express our answer in terms of kilobytes because this answer is in terms of bytes. So divide by this 1024, it comes 4 KB. So what is the right answer? Option A. That means 64 kilobytes and 4 kilobytes.